Alright, let's go. Main sequence star. Main sequence star is the stable beginning phase where stars spend most of their lives, and it's what our sun is right now. The core maintains a temperature around 15 million degrees Celsius, where hydrogen fuses into helium, creating outward pressure that perfectly balances gravity's inward pull. This equilibrium can last billions of years for smaller stars like our sun, but massive stars with 8 or more times the sun's mass burn through their fuel incredibly fast, living only 10 to 50 million years compared to the sun's expected 10 billion year lifespan. These massive stars burn blue-white and intensely hot, their cores churning through hydrogen at a furious rate. Throughout this phase, everything seems stable and peaceful, but the clock's already ticking toward an inevitable and spectacular end. Hydrogen depletion. Hydrogen depletion marks the moment when the fuel tank hits empty, and the star's stable life begins to end. After spending about 90% of its entire lifetime fusing hydrogen in the core, the star exhausts this fuel and leaves behind an inert core of helium ash. With no more fusion happening in the center, the core can no longer generate the outward pressure needed to resist gravity, so it starts contracting under its own weight. As the core shrinks to roughly half its original size, the compression heats it dramatically, pushing temperatures up toward 100 million degrees Celsius. This intense heat ignites a shell of hydrogen surrounding the dead helium core, creating a new fusion zone. The star is no longer in equilibrium, and gravity is starting to win this ancient battle. Red supergiant expansion. Red supergiant expansion transforms the star into an enormous bloated giant that can swallow entire planetary orbits. While the core contracts and heats up, the outer layers expand dramatically in response, sometimes reaching diameters over 1,000 times the star's original size, large enough to extend past Jupiter's orbit if placed where our sun is. The surface cools significantly as it spreads out, dropping to temperatures around 3,000 to 4,000 degrees Celsius, which gives the star its characteristic red color. Betelgeuse, the red supergiant in the Orion constellation, is a famous example currently about 700 times the diameter of our sun. Despite the cool surface, the core continues contracting and getting hotter, creating an extreme contrast between the star's frigid exterior and its blazing heart that's preparing for the final fusion stages. Onion shell structure. Onion shell structure develops as the star creates multiple layers of fusion, burning different elements simultaneously, like the layers of an onion. The core, now composed of helium, begins fusing into carbon and oxygen while a shell of hydrogen continues burning just outside it. As this process continues over thousands of years, more shells develop, with each burning a different element. From the center outward, silicon burns in the innermost shell, then successive layers burn neon, oxygen, carbon, helium, and finally hydrogen in the outermost fusion zone. Each shell operates at a different temperature and produces progressively heavier elements, with the hottest and densest conditions near the center. This beautiful layered structure represents the star's desperate attempt to keep generating energy and stave off gravitational collapse, but it's only buying time before the inevitable. Silicon burning. Silicon burning is the final fusion stage before catastrophe strikes, and it lasts an incredibly brief time compared to earlier phases. The core temperature exceeds 3 billion degrees Celsius, hot enough to fuse silicon nuclei into iron peak elements like iron, nickel, and cobalt. For a massive star that has lived for millions of years, this final fusion stage lasts approximately 1 to 2 weeks, a cosmic eye blink. The silicon shell burns with blinding white-hot intensity, producing primarily iron-56, the most stable nucleus in the universe. Once silicon fusion creates a core of iron and nickel, the star has reached the end of the line because iron cannot be fused to release energy. Instead, it actually absorbs energy during fusion. The star has unknowingly built its own death trap. Iron core formation. Iron core formation completes the ticking time bomb at the star's center, creating a structure that cannot be sustained. The core accumulates iron and nickel until it contains roughly 1.4 times the mass of our sun, compressed into a sphere about the size of Earth, with density reaching millions of times that of lead. This is called the Chandrasekhar limit, the maximum mass that electron degeneracy pressure can support. Unlike every element before it, iron cannot fuse to release energy because it sits at the bottom of the nuclear binding energy curve, meaning fusion would consume energy rather than produce it. With no energy source left to generate outward pressure, the core is supported solely by the quantum mechanical resistance of electrons being squeezed together. The iron core sits there for mere hours or days before the catastrophic collapse begins. Photodisintegration. Photodisintegration occurs when high-energy gamma-ray photons become so energetic they literally tear iron nuclei back apart into helium. At temperatures above 10 billion degrees Celsius, the gamma rays in the core possess enough energy to reverse billions of years of fusion in mere seconds, breaking iron-56 back down into 13 helium-4 nuclei plus neutrons. This process is catastrophically destructive because it absorbs enormous amounts of energy that was providing the last bit of pressure support holding the core up against gravity. The energy that took millions of years to build up through fusion gets consumed in moments, removing the final barrier preventing total collapse. Photodisintegration essentially kicks the last supporting pillar out from under the star's core, and what follows is the fastest and most violent collapse in the universe: Freefall collapse. Freefall collapse is 0.25 seconds of ultimate destruction, where the core implodes at an appreciable fraction of light speed. The iron core, previously the size of Earth, collapses down to a sphere just 20 to 30 kilometers in diameter in approximately 1/4 of a second. Matter falls inward at velocities reaching 70,000 kilometers per second, roughly 23% of the speed of light, creating the most extreme conditions of density and temperature in the universe outside a black hole. The outer shells of the star, still burning their various elements in the onion layers, have no idea this is happening yet, because the collapse occurs faster than information can travel outward. During this brief moment, billions of years of stellar evolution culminate in a gravitational freefall so violent that the very structure of matter breaks down. Neutronization. Neutronization is the process where extreme pressure forces electrons and protons to merge into neutrons, fundamentally changing the composition of matter. As the density climbs to about 400 trillion times that of water, electrons get squeezed into protons through a process called electron capture, creating neutrons and releasing floods of neutrinos that stream outward, carrying energy away. The matter transitions from normal atomic structure into neutron-degenerate material, where neutrons pack together as tightly as they do in atomic nuclei. The neutrinos produced carry away vast amounts of energy, actually robbing the core of the pressure support it desperately needs. By the time the core reaches nuclear density, it's no longer made of atoms at all, but rather a uniform soup of neutrons. And this marks the birth of what will either become a neutron star or collapse further into a black hole. Core bounce. Core bounce happens when the collapse violently stops at nuclear density and the core rebounds like a rubber ball hitting the floor. When the density reaches approximately 2 to 3 times nuclear density, about 400 trillion grams per cubic centimeter, neutron degeneracy pressure finally becomes strong enough to halt the collapse. The inner core, compressed to its absolute limit, rebounds outward in milliseconds, but it runs headlong into the outer core material that's still falling inward at tens of thousands of kilometers per second. This collision creates an incredibly powerful shock wave that begins moving outward through the star, carrying about 10 to the 51st ergs of energy, a unit astronomers call a foe. The proto-neutron star at the center is born in this moment, but whether the shock wave can make it to the surface and actually explode, the star remains uncertain. Shock stall. Shock stall is the moment when the first explosion attempt fails and the shock wave loses its momentum. As the shock moves outward, it encounters infalling material and uses tremendous energy to break apart the heavy nuclei in its path through photodisintegration, ironically the same process that helped trigger the collapse. Within about 0.01 seconds, the shock loses roughly 99% of its initial energy and stalls at a radius of approximately 150 to 200 kilometers from the center. The shock hangs there, neither advancing nor retreating, surrounded by material still collapsing inward from the outer layers. Without some mechanism to revive it, the shock would fail completely, and the outer layers would fall back onto the core, producing a weak explosion at best, or possibly just forming a black hole directly. This is one of the most critical and mysterious moments in the entire supernova process. Neutrino torrent. Neutrino torrent carries 99% of the explosion's energy in the form of nearly invisible particles that flood out of the collapsing core. The newborn proto-neutron star releases approximately 10 to the 58th neutrinos over about 10 seconds, carrying away roughly 10 to the 53rd ergs of gravitational binding energy. For this brief period, the neutrino luminosity of the core exceeds the combined light output of all the stars in the observable universe, even though these neutrinos are so weakly interacting that most would pass through an entire light year of lead without touching anything. On Earth, when supernova 1987A exploded in the nearby Large Magellanic Cloud, detectors caught about 24 neutrinos out of the trillions that passed harmlessly through our entire planet. Despite their ghostly nature, this tiny fraction of neutrinos that do interact with matter behind the stalled shock will prove crucial for reviving the explosion. Shock revival. Shock revival happens when neutrinos rescue the stalled shock and push it outward again towards success. Even though neutrinos interact incredibly weakly with normal matter, the density behind the shock is so extreme and the neutrino flux so intense that about 0.5 to 1% of the neutrinos deposit their energy into the material there. This may sound like a small fraction, but it still represents about 10 to the 51st ergs, an enormous amount of energy. The deposited energy heats the material behind the shock, creating turbulent convection currents that help drive matter outward and break up the spherical symmetry. Within approximately 0.1 to 1 second after the stall, this neutrino heating reinvigorates the shock wave, and it begins accelerating outward again. The explosion is back on track, and the star's outer layers are finally doomed. Explosive nucleosynthesis. Explosive nucleosynthesis is the universe's heavy element factory, where the shock creates conditions for the rapid neutron capture process that builds elements heavier than iron. At temperatures around 5 billion degrees Celsius and neutron densities reaching 10 to the 24th per cubic centimeter, neutrons slam into atomic nuclei faster than the unstable nuclei can decay, building up elements like gold, platinum, uranium, and thorium. This R process, short for rapid neutron capture process, is one of the primary ways the universe creates elements heavier than iron. The explosion also produces approximately 0.1 solar masses of radioactive nickel-56, which will power the supernova's visible light in the coming weeks and months. All the gold in your jewelry, the platinum and catalytic converters, and the uranium in nuclear reactors was forged in these extreme conditions during the final seconds of dying massive stars. Shock breakout. Shock breakout is the dramatic moment when the shock wave reaches the star's surface and first light escapes into space. Hours to days after the core bounce, depending on the star's size, the shock plows through the last layers of the stellar envelope and breaks through the surface. The material suddenly becomes optically thin, meaning photons can escape freely instead of being trapped and scattered. This produces an intense flash of ultraviolet and X-ray radiation, as the shock-heated material at temperatures around 200,000 Kelvin suddenly becomes visible. The UV flash lasts for minutes to hours, and reaches luminosities around 10 to the 43rd ergs per second. For astronomers lucky enough to catch this brief event, it provides crucial information about the star's radius and structure, but it requires monitoring the right patch of sky at exactly the right moment. Peak brightness. Peak brightness occurs days to weeks after the explosion, when the supernova reaches maximum visible light and can outshine an entire galaxy containing billions of stars. For Type 2, supernovae from massive stars, peak brightness typically arrives about 10 to 20 days after the explosion begins, reaching absolute magnitudes between -17 and -19, which means if one occurred in our galaxy, it could be visible during daylight. At peak, the supernova can reach luminosities around 10 to the 43rd ergs per second, briefly rivaling the output of billions of normal stars. These objects are so bright that astronomers regularly spot them in galaxies millions or even billions of light years away, making them crucial tools for measuring cosmic distances and understanding the universe's expansion. After peak brightness, the supernova begins its long fade, but even that dimming carries important information about what happened in the explosion. Radioactive afterglow. Radioactive afterglow powers the fading light of the supernova for months after the initial explosion through nuclear decay chains. The radioactive nickel-56 produced during explosive nucleosynthesis decays into cobalt-56 with a half-life of 6.075 days, and then the cobalt-56 decays into stable iron-56 with a half-life of 77.27 days. Each decay produces gamma rays with energies around 2 million electron volts that heat the expanding debris, causing it to glow in visible light. This radioactive decay essentially acts as a dimming battery that keeps the supernova visible for months, with the light curve following the characteristic 77-day cobalt decay timescale. The expanding material gradually becomes transparent to the gamma rays, allowing them to escape, which causes the visible light to fade with a characteristic exponential decline. By studying this light curve carefully, astronomers can determine how much nickel-56 was produced and learn about the explosion's energetics. Remnant formation. Remnant formation creates one of two exotic objects, depending on how much mass the core contained after the collapse. If the core mass is between approximately 1.4 and 2.5 solar masses, it becomes a neutron star, an object about 20 kilometers in diameter, but containing more mass than the Sun, with density equal to that of an atomic nucleus at roughly 10 to the 14th grams per cubic centimeter. These neutron stars spin rapidly, sometimes hundreds of times per second, and possess magnetic fields trillions of times stronger than Earth's, reaching 10 to the 12th Gauss or more. If the core mass exceeds about 2.5 solar masses, not even neutron degeneracy pressure can support it, and the core collapses further into a black hole with an event horizon radius between 6 and 30 kilometers, depending on the math. Either way, the collapsed core represents the most extreme state of matter in the universe. Supernova Remnant. Supernova Remnant is the expanding debris field that the explosion creates, sweeping up interstellar material and enriching the galaxy with heavy elements for centuries to millennia. The ejected material races outward at velocities between 5,000 and 10,000 kilometers per second, roughly 1.5 to 3% of light speed, plowing into the surrounding interstellar medium and creating a shock-heated shell that glows across the electromagnetic spectrum. Famous examples include the Crab Nebula from a supernova observed in 1054 AD and Cassiopeia A from an explosion around 1680. These remnants remain visible for approximately 10,000 to 100,000 years as they expand and gradually fade, eventually merging with the interstellar medium after releasing 10 to 20 solar masses of processed material enriched with carbon, oxygen, silicon, iron, and heavier elements. This material becomes part of future generations of stars and planets, meaning the atoms in your body were likely forged inside dying stars billions of years ago.